All right. So just moving on to the next part of the program, which is the industry talks, and we are very pleased to have as the first speaker Chris Dick from NVIDIA, and of course, Chris knows everyone. Everybody knows Chris, so he doesn't need an introduction. But just to summarize his many qualifications in 2 sentences, so Chris has really shaped and followed the transformation of the wireless industry from the 3G, 4G, and 5G standards. And currently, he's a wireless architect at NVIDIA, and he's really driving the AI ML vision for future 5G and 6G standards. So, with that, Chris, the podium is yours. Thank you very much for joining us.
Great. Thanks, Kashik. Thanks for the opportunity to present today. I'm not sure, are my slides showing or not?
Yes, we can see them.
Okay, great. And can I do a time check? Because I think we're over. Have I got 20 minutes?
Yes, please go ahead, 20 minutes.
Okay, great. So AI/ML is a cornerstone technology from NVIDIA and wireless, and as such, data collection, curation, query, high-performance processing is key. So today, what I wanted to do is give a little bit of a preview of some of the tools and technologies that NVIDIA currently has in development to support wireless research. In particular, I'll kind of zoom in on some of the things that are in flight around data collection. Okay, so there are six main themes to how we're looking at enabling beyond 5G and 6G research. One thing is to really double down on this area of big data meets wireless and embrace new platforms for data collection, data sharing, to enable, in particular, AI/ML research in layer 1, layer 2 of wireless systems, spectrum sensing, network slicing, online training, deep reinforcement learning, transfer learning, federated learning, and closed loop control of nodes in the system. To do this, what we have developed is a research VRAN, or a VRAN. It's also used for commercial engagements as well. But this commercial VRAN is 5GNR, fully 5GNR compliant. So everything is software. So layer 1 running entirely as CUDA code on GPU. Source code available for people that want to be able to experiment down at the physical layer. A open source layer 2 by virtue of OAI, and all working with COTS, 5G, and RUEs. The entire system from layer 2 to layer 1 through to the frontal interface is software defined. So we support, we're very much in the world of ORAN and 7.2 functional split, and using a NIC, or what we call a DPU, data processing unit, for supporting the frontal interface to many radio nodes. The fourth theme is in the area of new sets of tools for enabling native AI/ML from the outset. So I have a few slides on that later, but think signal processing library written in TensorFlow, where nearly all of the blocks are natively differentiable. So you can compose systems and backpropagate through a composition of signal processing blocks if you're in that world of experimenting with the application of neural networks to the physical layer. We put it all together under an umbrella that we call the research platform, which takes the VRAN and extends it with new pieces of the software stack, initially data collection, and then eventually the RIC. Another piece that I've got a few slides on the end is that I think when we talk about data collection, obviously the OTA, the over-the-air facet of that, and the harvesting of data from real networks, from IQ samples through to network level is important. But I think there's also an increasing role for high fidelity data sets generated by virtue of digital twins supporting RF-based ray tracing. We put it all together, we see this stack, aerial research platform, where the concept here is to be able to provide a suite of software and hardware that takes a researcher from algorithm design and rapid prototyping through to implementation on a test bed, and then ideally field trials, and if you're in the commercial area, potentially deployment. The top of the stack is this TensorFlow-based toolchain that was released several months ago called Chiona. Different wrenchable library. And then another facet of this is GPU accelerated from the outset. So there've been a few comments in the last few days around massive amounts of data, where do you store it, but also how do you compute on it. So these libraries are intended to run on large GPU clusters. You can, of course, it's all CUDA code under the hood. So of course you can run on a single GPU, but it's very easy and extensible to be able to run on large configurations of GPUs. A data collection layer that I'll show an image of in a minute. Digital twin technology based on a software framework that we call Omniverse, and that we're extending with RF-based ray tracing. It's been used extensively in many different application domains that have focused on light transport. So we're bringing to center stage here RF-based ray tracing. Then we move closer to Genode B. So Genode B software stack consisting of GPU inline accelerated layer 1. So we call it Aerial. I didn't mention that before. I think project name is Aerial. And then on top of this in blue, third-party layer 2 stacks, and depending on whether it's commercial orientation or research orientation, could be proprietary. One of the usual suspects that build commercial grade layer 2s, and then open source research OAI style layer 2. At the bottom layer is a hardware stack with, at this point, Ampere class GPUs, NIC for the front hall interface, and CPU for layer 2. Here's a figure which is, let's see if I can, it's annoying. Let's see if I can remove it. Okay, I guess I can't. A figure of our vision of this test bed that we're putting together. At the moment, you can think that what we have internally and soon to be stood up at one external partner is server, DU, layer 1, layer 2, NIC front hall interface, and then a switch connection out to a multiplicity of ORUs, grandmaster clock, and then the ability to be able to extract IQ data from each of the antenna elements in the ORU via port replication or port mirroring through this switch into a data collection agent that is running on what I've called a telemetry server here. So another server that's consuming data here and is running some custom software that we've had in development, and it's actually leveraging some of the data center scale class software that NVIDIA already has for several other projects to be able to deal with high volumes of data and be able to efficiently store data in its most compact format and most accessible format for access by GPUs and also CPUs. The first version of this system is data collection through this path, the data collection server, which also, actually I didn't mention it, as well as IQ samples, we extract what I'll call layer 2 meta information. So you have some notion of semantics of the data that you're collecting when you finally drop this data into a Parquet database, and then you have something to work with offline for data analytics, AI ML research, layer 1 algorithm development, layer 2 algorithm development, and so on. Future steps will extend this system to embrace the ORAN non-real-time and real-time RIC and the data collection nodes in that constellation, O1, A1, and E2 interface, so that you'll have a richer data set here from not only IQ samples, L2 meta information from the Genode B, but data from the RIC, and then eventually the ability to close the loop in what I'll call a real-time manner. So abilities to be able to do offline research, but capabilities to be able to do online research. So one might put together, let me see if I can just pick something here. Just trying to see if I can you might be able to, here's a kind of a realization of a system that you could construct with these components. And here I've rendered a test bed that has a focus on deep reinforcement learning. So over, oops, I lost my pointer here. Over here, we have just conventional edge servers equipped with NICs for frontal interface, GPUs for layer 1 signal processing, and CPUs for layer 2 and other processing. And then the data collection stack for being able to extract stateful information from the system and bring it back around into an environment. This environment could be a digital twin environment, doesn't have to be. Could be a digital twin environment, but some environment where you could be taking the state information, performing training or inference or other sorts of processing, and in a closed loop online manner, be able to return computer results back into the system, probably by virtue of the RIC. In parallel, you could be also recording the activity in the system and creating data sets that could be pushed out to RFDataFactory, for example, together with reference PyTorch code and so on and so forth. The way we have elected to represent our data is to borrow from the small cell forum FAPI interface, so functional application platform interface here. So normally something that people would look at as an API between layer 2 and layer 1, but this same data model can be useful for being able to represent wireless data in a database. So here's an example here. So here's an example of what the data model looks like for an uplink TTI request. So system frame number, slot number, number of packet data units, information about the RATch, and so on. So in our database, all of these data fields are accessible in that database. So one could be storing data over long periods of time and be able to reach back into the database and query it to be able to extract, for example, please return to me all slots that were using 16 QAM, or please return to me all demodulation reference symbols from last Thursday morning between 10 a.m. and 10:30. So it's a fairly rich data model that is sitting under the hood here, and it's accessible to everyone, right? SCF FAPI spec is pretty well defined, and anyone can access that spec and understand how it works. On top of that, so there's kind of one piece around setting up the telemetry structure for being able to collect data from all levels of the network, from IQ samples initially, but eventually moving up the stack to be able to collect data at the network level. And then it's a step of processing the data. So I've given one example here where we already have sophisticated software stacks that are used for data science in other fields that already heavily use ETL pipelines and sitting on top of Apache Arrow, processing Parquet files and different software modules that support various types of pre-processing, which can be potentially time consuming in many cases, different flavors of machine learning, and so on and so forth. And then in addition to that, inbuilt parallelization via Dask. So parallelizing pandas or NumPy or SciPy so that you can do data query, data pre-processing, machine learning training easily parallelized over large GPU clusters. The next piece of the tool chain is very specific to wireless. So this is Xiona. So Xiona was built to enable kind of a new generation of wireless research at the link layer. Written natively in TensorFlow and with GPU acceleration as a first-class consideration, the goal of Xiona was to be able to enable machine learning and AI research easily in TensorFlow. So this stack here gives you a little bit of flavor of what Xiona is about. So every component is TensorFlow is a Keras layer, right? So you can compose layers together, and every one of these components is differentiable. So you can form backpropagation through the composition of signal processing blocks. All data that's moved between functional blocks are tensors. So there's no for loops here, right? So in the spirit of compute efficiency and timeliness, everything is carefully constructed as a data tensor, and data tensors are moved between functional blocks. Default data type is TF complex 64. And there's different flavors of execution models. So for initial experimentation, it supports TensorFlow eager mode of execution. For highest performance, graph mode of execution. And then here's that story around GPU acceleration, and also highlighting there's completely open source. So all of the code for all library components here are on Git, which is, I think, very useful. It seems to have attracted quite an amount of interest so far from the research community. Just switching gears for a little bit. So another piece that we think is central to enabling wireless research, and also not disconnected from dataset production, is digital twins. So digital twins, we think, will be a huge part of the future. It's already playing a huge role in many different disciplines, from training robots to automation in warehouses to planetary scale models for predicting climate change, industrial modeling, and we use it heavily in NVIDIA as part of our autonomous vehicle program for building data sets for training autonomous vehicles, the many different machine learning models using autonomous vehicles. In the last 18 months or so, we've seen RF planning and network optimization being done by Ericsson. So the use of a tool that we call Omniverse for use in the wireless space. So just as we've seen this tool Omniverse, right, which was built specifically to enable virtual worlds and digital twins, just as we've seen it used in the vehicular space with something we call Drive, and in the robotic space, which in NVIDIA parlance is Isaac, and then another product called NVIDIA Avatar, and then NVIDIA Earth 2, we're extending Omniverse to be able to bring in CAD models of topologies. Here's a corner of San Francisco, and be able to extend the light transport ray tracing to RF capability so that you can collect data sets that I would claim are high fidelity from these simulation environments. And then the platform offers a capability to bring all of these virtual worlds together. So the combination of the drive sim, digital twin, and camera sensors, and LiDAR, I can't get my pointer here, and LiDAR sensors, bring it together with the world of wireless to enable, in the bottom right-hand corner here, digital twinning in, for example, Industry 4.0. That bottom right-hand is actually a photorealistic image in Omniverse, right? And it's and you could well imagine on the factory floor sensor fusion being applied for robots, camera, location, LiDAR, and spectrum management, all happening in the context of digital twin. So to conclude, obviously over the air and network data collection remain key aspects of 5G advanced, 6G and 6G research, and eventually deployment, because ultimately we believe that the data collection framework will actually be part of the base station, and that the data collection will be used for making site-specific optimizations in advanced base stations. So it won't only be a tool for research, it will be a tool that will enable deployment. Offline processing remains important and critical to advance research. And as we move forward, I think the ability to bring closed loop control into the picture, into these test beds, so one can do sophisticated experiments with deep reinforcement learning and be able to collect state information from a testbed system and be able to do online training and return control information and actions back to the system, I think will be important. Another part that we think will be important is being able to maybe moderate the size of a data collection campaign and augment real world data with statistically equivalent samples, or samples that can't be that can't be differentiated from the original statistics of the environment using generative adversarial networks. And we also believe digital twins and ray tracing will augment research and augment the construction of databases and sit alongside over-the-air captured databases. Okay, that's it.
Chris, thank you very much. And at this point, I'd like to open the floor to questions. Perhaps a quick question from anyone online, if there is one. Just want to make sure that we don't miss any of the online questions. Well, if not, questions from the audience? So Chris, I have one question that I'd like your thoughts on. So you mentioned digital twins and several such additional use cases. Do you see the twin working in real time, or is the twin purely an offline step which replicates the physical world before deployment? And should you think it is online, would or are we there where we can process and compute in that kind of a real time?
Yeah, so to me, I would observe that maybe the term digital twin is thrown around in various contexts, and sometimes it's used maybe interchangeably with simulation. I would say the ultimate and the real digital twin is when you have that closed loop engagement between the physical world and the cyber rendering of that world, and that you have those mechanisms to be able to move data from the physical world to the cyber world. Then I think it becomes a matter of, then one might ask, well, how much data can you expect to move if you're a network operator, right? Moving for a minute to, I'm a network operator and I'm really going to employ a digital twin for control and optimization and monitoring and troubleshooting my network. Then I think it becomes a question of, pick your problems. You're probably not going to be capturing IQ samples from every antenna or from every base station across the whole, whole of San Francisco, but you could plausibly be extracting network and packet level data into a digital twin. And when we see some of this, in fact, later this year, we'll see some omniverse-based, very large-scale digital twins that that will be announced. So it's plausible, right? There's a lot of data movement capability in a data center with these very powerful deep data processing units, DPUs. So you can move a lot of data, and you can deal with digital twins of large systems.
That's fascinating. In fact, we'll be sure to follow the ODD developments with Omniverse. And this is one of the most fascinating things that we have seen from NVIDIA in a while. Other questions from the audience, if there's any final question? Well, if not, then Chris, thank you very much for joining us. We might keep in touch with you for other questions, perhaps in the chat if you are going to be there for the rest of the program. But thanks again for your vision and for being here. Thank you.
Thank you.
So we'll follow up with a second industry talk by today, and we are very pleased to have Dr. Subhramoy Mohanti from InterDigital. Subhramoy is a research and innovation researcher in the Emerging Technologies Lab at InterDigital. He has won many awards, including the Infocom Best Paper Award in 2018, and has true insights on the system side of wireless research. So with that, Subhramoy, your podium. Thank you for coming.
Thank you, Kaushik, for inviting me here. And thank you, everyone. Thank you, everyone, for being here, too. So yeah, I'm Subhramoy Mohanti. I am a researcher at InterDigital in the Emerging Technologies Lab. Yeah, as a part of our research in this lab, we work with like new ideas, innovative, like new exploration, new topics in the area of like wireless and video domains. And we also try to explore like what are the avenues of research you can go into for the next generation of wireless and video research areas. And like AI or artificial intelligence plays a big role in our research, actually in the lab that I work. So as you can see, we are hungry, we are always hungry for more RF data. So that's where this interest comes in. Like this is a really good initiative, this RFDataFactory, where people are trying to assimilate diverse sets of data from all around the world into under one umbrella. So there's a really good initiative on this part. So of course, like with this initiative comes some issues and concerns that we discussed as a part of this workshop, and what I want to try to like put forward, that if we address them as we are building this RFDataFactory, I believe it is going to be really it is going to help us understand the true potential of this RFDataFactory. So going forwards, what we have is that the one main question is the richness of data, right? Like how much data is good? Is it like the more the better the answer? I mean, like, is that the way we want to go forward? And also like that leads to the question that the data storage cost, right? And the ML training cost in terms of time and energy consumed, and versus the accuracy of prediction. Right, so here I can say like the AI of today is like a gas guzzling fuel truck or like like a pickup truck, and we want to take it to the point where it is an energy efficient, fuel efficient vehicle. So that's where the AI can do much better with less amount of data, and that will lead us to this problem of like, okay, because I saw a presentation yesterday where someone was saying like, okay, we are generating data like gigabytes of data like a few years ago, but the same types of experiment today costs us like terabytes or exabytes of data. Like, and now that is just one experiment, right? Now, if we have researchers from all around the world who are trying to generate data, and then we want to store it under one umbrella, like where do you store it, right? So that's the first concern, like if we can address that, like make AI more efficient, and also see like how much data we want to have so that it can be used by multiple ML sub-processes. That's like one way of addressing these issues. The second one is the privacy concern, right, that we had. We want to generalize data because we want to protect people's privacy. But of course, like how much generalization do we want to do? Because we also want to come up with better solutions for the future. And so there is a trade-off there also. And how much generalization will be needed for that, so that the data set that we have at the end can be used by multiple researchers across multiple domains. So we need to address that concern also going forwards. And this RFDataFactory can be a good platform to start the discussion. And also, like when we have like a diverse set of like users generating data, collecting data, and putting them in one place, and they are distributed set of users, that leads to the point where we want to say like, okay, this needs to be understood by everyone that we're trying to use this data. So we need to have this commonality between APIs, and we need to have good documentation. So that when we go and see this data set, we know what it is and what it is going to be used for, and if it is going to be useful for our own research. And so when we use data sets in our own research lab, because we are primarily like focused on publishing new ideas and submitting patents, we look to see if there is relevant data out there in the world, because our research lab, as a few people, we cannot generate as much data as we want. So there is a huge overhead from my own experience, that we have to. There is no good documentation. There is no good catalog of all the wireless RF data that is out there, and we have to like go browse through the internet to see like, okay, if this data is good for us or not, and then we have to do trial and error to see if we can actually use it for our own research purposes. So that leads to the question that can we use this RF data factory in that way that we can say like, okay, we can just go there and we can find what we want with the minimum amount of overhead in the process. So then also this comes the process of the standardization, right? Like in academia, I have seen, as I was a PhD student, we mostly collect data using off-the-shelf hardware like SDR radios. But then in the commercial arena, the industrial arena, we have totally vastly different numbers of hardware, different types of hardware. And those hardware are like can we say like the data that is collected from that hardware is similar to the data that is collected in academia through SDR radios and other similar software-defined radios. So if we can make an apple-to-apple comparison, that will lead us to make sure that whatever solutions that we are coming up with from an industry perspective, that will go into the standard bodies, like they can be that can be done on the reliable sources of data. So that is one question that we can try to address for this wireless RF data factory, where we can say like, hey, like this data set was collected with this hardware, this was the amount of work done on it, and people have used this for this kind of work. That will really help us to understand that, okay, we can use this for our own research also. And also like the maintenance, right? Like, okay, you have different platforms collecting data, right? And can you ensure that all the platforms are maintained in a proper way, and there is not much like noise or other kind of interference things coming up and kind of corrupting the data, and make sure that whatever data is out there in this wireless RF data factory, they are what it is, right? What it is supposed to be. There is not much corruption of the data there. Because at the end, when we are in the process of doing our research, towards the end, if you see like, oh, this was not actually relevant for our own work, that will let us to like go back to the drawing board, and that will lead us to lose confidence in this entire enterprise, right? So that is one way we can ensure that there is more industry collaboration in this process of this RF data factory. And yes, like we like to collaborate with industry, academia. But I heard the question that was mentioned, that there needs to be more industry involvement in this process. But from my own experience, what I have seen is that as from the industry perspective, we also collect a lot of data, but we do that with licensed software from multiple other vendors, and we also sign a lot of NDAs with other third parties. So if we'd want to share the data with you, but our hands are actually tied in this process. But also there's a way going forward where academia can send more interns. We're always looking for internships, interns to come to work with us, and that way academia can also gain an insight into all the data that we have collected with commercial, like commercial hardware, and that way we can actually lead some collaboration efforts in that process. So this is actually a very good venue to address these issues, to discuss all of these issues, and I believe that going forwards we can do a really good job in this process. And thank you again, everyone. Thanks.
Questions for Subhramoy?
The last comment you made together with the previous talk sort of prompted a question, which is, you mentioned that you have lots of data from commercial hardware that then somehow involved an NDA from the hardware vendor that blocks the sharing of that data.
Exactly.
Do you think that the approaches of synthetic data generation based on real data sets that were talked about kind of yesterday in the context of privacy. And here, kind of in the previous talk, talked about in the related to the idea of digital twinning, do you think that that can be used to overcome the NDA issues here when it comes to vendors?
Yeah, that's a good point. So yeah, digital twins and synthetic data, they are emerging areas. So we want to also try to understand the reliability of the synthetic data, right? So we need to do more research into those areas. We ourselves in our lab are doing more synthetic data generation and trying to compare the actual data sets versus the reliable data sets, how much performance difference is there in terms of reliability and in terms of accuracy. And that is actually a part of our core research area, because obviously, like, still this point, as an industry perspective, we believe that real data is the way to go forward. But of course, we welcome synthetic data also in this process, and if it is proved to be as efficient as on the real data sets, we are going to go with that process also, and that will lead us to not these red tapes, to overcome these red tapes of like NDAs and other stuff, and we can have more collaboration in the process. But then, yes, we that's like we need some time, right? Like from academic perspective or industry perspective to understand the validity of this synthetic data kind of questions.
So to follow up, if there's not another question,
Yep.
To follow up, I think one question that of course is there with synthetic data is, is it actually valid?
Right.
The other question is, if I literally have a workflow that is, here's data under an NDA, I generate synthetic data following some protocol from this. The output is now no longer covered by the NDA from the vendor.
Mm-hmm.
What's the distortion metric needed to essentially escape NDAs vis-a-vis data? Is that something that, it seems like it's a bottleneck that you've identified for data sharing, so it seems like that's an important topic to work
because for example, in cell phones, right? Like we have Qualcomm chipsets, and you also have the network vendors, right? Like T-Mobile and AT&T. So each one of them have their own algorithms and have their own header information in the data packets that we're transferring through over the air. So now, as a research lab, when we want to go into the standard bodies and say hey, this solution actually will be better than the existing one, we have to show them that, okay, what is the existing performance? And for that, we need that type of information that is licensed by these companies, right? Now to show that our solution is much better, if we can do that with synthetic data, that needs to be validated from the actual mobile equipment vendors that, hey, actually, this is actually the one that we also did, right? The same apple-to-apple comparison. And from their perspective, there is this incentive not to do that, I think, because, it's in a capitalist world. So I think but the thing is that there is a way to go around this, right? We cannot just fight it. We can go around it, I believe, because we always want to do high quality publishing and patenting, right? So I think if we can somehow make sure that the synthetic data is as good as the existing performance indicators of the current mobile network operators and performs at par with our research, I think that way we can start, carrying forward this conversation. And also, I think one good way of going forward is to have more academic involvement in the standard bodies, right? Like in 3GPP or 802.11 wireless standards. I do not see that amount of participation from the academia, right? So if we can go with that area, that way we can actually have our own, academia can have its own say also in this matter. Thank you.
So in closing, I have one more question, So the way I understand this, and this is to both you, Subhramoy, as well as Chris, who hopefully is also online. The question is, it seems to me that one needs to be part of an exclusive club where there are NDAs signed, specific licenses acquired, and that is really hampering free industry academic collaborations. So could this be a possibility that we form such a club where maybe there are a list where we know, look, here are these academic licenses that exist that allow an academic to go and use them only under these conditions. Here are these NDAs that must be signed. So we have a charter of these requirements. Such a club is formed, and now freely within that group of people with pre-negotiated and signed agreements, there is free exchange of data between industry and academia and sort of really grow and make access. I'm just throwing this just as a possibility. Is that even within the realms of possibility, or just still fiction? Why don't you take, and then we'll ask Chris if he's there.
Yeah, thank you, Kaushik, for this good insight. And I believe that, yes, like everyone likes good ideas and everyone wants to create something new, right? A new splash. So I think going forwards, if we can involve the FCC more in this process and say like, hey, academia has a lot of like, good minds, and there's a lot of research going on in this area, and you guys can also contribute a lot compared to a select club of, like companies. And that will lead to better solutions and better progress going forward. I believe that actually we can start this process, and then it will lead to better solutions in the future.
Thank you. Thank you. Chris, any concluding thoughts on that question? Can we form such a club where licenses and NDAs are pre-executed, and there's a freely allowing people to talk? Chris.
Yeah, I'd like to be part of a club. If it has a good espresso machine, that'd be great. How do I answer? I guess we're kind of looking at it from, we want to democratize, to use a overloaded word, this whole notion of data collection, data processing, and open source. Many of the things we do, if it takes a club to kind of crack that chestnut, I guess, but and I'm sure we would be willing participants, but we're kind of looking at ourselves as the providers of the platform. And then other people are collecting the data. So I don't know whether it's too much in NVIDIA's shop, but it's certainly open to anything that's going to help broaden, make more sophisticated, make more powerful data collection, and then also the tools, right? All the other tools for processing. I think that's about all I got for you, Kaushik.
No, absolutely. I think this is just a start of a long conversation as to how to be effective partners between the academic and industry. And this discussion is going to come up in every panel, in the lunch discussions, in the coffee breakouts, I'm sure. So with that, I must thank you both, Subhramoy and Chris, for sharing these insights. Thank you very much. And so right now,